Hello everyone, welcome once again to our discussion on the optimization problems, maxima and minima. Okay, so last time we talked about the concept on how to solve optimization problems. So we need to follow some procedure and apply some principles that we have learned in our previous topic, especially the extreme value theorem. Okay, so this time we are going to solve some sample problem. So this is the problem that I have shown you last time. So we have a closed box with a square base is to have a volume of 2000 cubic inch. The material for the top and bottom of the box is to cost 3 cents per square inch. And the material for the sides is to cost 1.5 cents per square inch. Determine the dimension of the box. So the total cost of the material is list. Okay, so first we need to write down the givens to help us analyze this problem class. Okay, so given in the problem, so the box is to have a volume of 2000 2000 cubic uh, inches. Okay, so we're given the volume. So the volume is equal to 2000. So what else are given in the problem? So this is 2000 cubic inch. And we're given also the cost for the top. So cost of the material for the top of the box. So we're given 3 cents. This is 3 cents. It's 3 cents per square inch. And for the bottom, so for the bottom it's the same. So we are given the cost of 3 cents 3 cents per square inch. And for the sides, so for the sides, so the cost is 1.5 cents. All right, so these are the given in the problem, and we are asked to solve, or we are required to solve for the dimensions. So what does it mean, class? Dimension. So if you have the box, so what are the dimensions of the box? What are the dimension, class? Okay, so this is the requirement in the problem. So we need to find the dimension. Okay, now for our solution, I'll present it in another another screen. Okay, so for our solution, okay, so the best thing to do is to make an illustration, because illustration will help us according to the concept on how to solve optimization problem. So it's very helpful because if we can illustrate something to represent the thing that is mentioned in the problem. So in this case, uh, we're given a problem that talks about box, closed box. So assuming this is our box, okay, so assuming that is our box. So the problem says the box, a closed box, has a square base. Okay, so what does it mean, square base? So if it has a square base class, so it means that we can let this side here be equal to x, or you can represent it by any variable you want. So if the base is square, so it means if this is x, so this is also x. All right. Now, since the problem says closed box with a square base, it didn't say that it is a cubic box. So it means that if this is x, this is x, this is not x, right? This should be a different dimension. So we can call this as h. Okay. So this is the base. All right. So this is the base, and this is the top. Okay. So this is the top of the box. Then next thing to do is to express, no? In the problem we are, it says that the total cost to be should be list. So it means that we are going to optimize the cost. Okay, so we are going to express the cost in terms of dimension of this box and also the cost of the material that we are going to use to make this box. Okay, so we have let C be the total cost. All right, so total cost as a function of, then look at our box. So our box here contains two variables. We have x and h. So the cost is a function of the variable x and h. Okay, so this is our cost function equal to. So of course we are talking of cost. So we're given the cost of the top, that is 3 cents per square inch, and also the bottom 3 cents per square inch, and the side is 1.5 cents per square inch. So when we speak of cost, the total cost should be in terms of cents. So it means that since the top, okay, the top, we have, by the way, if this is x, since this is parallel to this one, so this is also x, okay, and since this is x also, and this side is also parallel to this one, so this means this is also x. Okay, so now for the cost, so since the unit given is in 3 cents per square inch, so to get a unit of cents, so we are going to multiply that per unit or per square inch cost by the area. Okay, so we multiply that by the area. So the area of the top, so area, this is a square, so area of the square is just the product of this two sides. So this side x multiplied by this side x, or simply x times x is equal to x squared. All right. So the unit of this is in terms of square inch. Okay. Then multiply this by the cost. The cost is 3. 3 cents per square inch. So the unit of this 3 is cents per square inch, and this one is square inch. So therefore, square inch will be divided by another square inch. So that's equal to 1. So the cost here will be in terms of, I mean, the unit of this product is only cents. Okay, so that's for the top. Then plus, so the bottom also a square. All right, so this is also x squared, just the product of the two sides. So when you look at the area, when you find the area of this bottom, so just multiply the sides. Okay, and the cost, that is also 3 cents. Okay, 3 cents per square inch. Then plus, right? So we have the sides. So what are the cost, or what is the cost of the side? By the way, class, how many side here? So we have here this side. Okay, we have here side 1. All right. We also have this side here, side 2, and we have it here, side 3, side 3. Okay, and then we have here side 4. So it means that we have 4 sides, meaning the box has 4 sides. Okay, so what's the cost of the side? So the cost of the side is 1.5. So the cost of the side is 1.5. Okay, so again, the area of the side is just the product of this length and this length here, or this is the width if you consider this as length, width, and height. So to find the area of this side here, so this is just the product of x and h. Okay, so just the product of x and h. So therefore the area is x times h. Then multiply this by the cost of the side. The cost of the side is 1.5 cents per square inch. Okay, but there are 4 sides, right? We have side 1, side 2, side 3, side 4. So therefore we have to multiply this by 4. Okay, so 4 times 1.5 times x times h, or we can combine similar terms here. So we can combine this, so they're just similar. So we have 6x squared, then plus, So multiply 4 by 1.5, so that is 6. 6 times x times h. Okay, so this is our cost as a function of x and h. Okay, we can call this equation as our equation 1. Then the technique here, class, to make it easier to solve, we have to express the left side, meaning the cost, in terms of a single variable. Alright, so that's much better, no? If you can express our function in terms of a single variable. So in this case, we can express x in terms of h, or h in terms of x. So how will we do that? So to do it, let us use this concept here for the volume, because volume is given, right? So since this is a box, so from our solid mensuration, can you still remember that solid mensuration, your previous mathematics? So if you have a box or something in a cubic form, or something like this, a solid, so we when we are asked to solve for the volume, we simply multiply the length, the width, and the height. Or volume of the box is just the product of the length, the width, as well as the height. Okay, so that is the general formula for a volume of a box. Okay, so volume. So from our illustration, what is our L? So from our illustration, this is our length. We have x. Then our width is also x. So x times x. Then our height is equal to small h. Or volume is equal to x squared times h. Okay? But given in the problem, class, that the closed box is to have 2000 cubic inch. So therefore, volume is 2000. So we can make use of that given. Now substituting that value into our equation here. So 2000, that is the volume. Okay, 2000 equal to x squared times h. Okay, so from here we can solve for h in terms of x. So solving for h in terms of x, so we can divide both sides by x squared. So we have, then just interchange the sides. So we have 2000 divided by x squared. Okay, so we can call this equation as our equation 2. Alright, so if we are going to substitute, if we are going to substitute equation 2 in equation 1, okay, I'll just abbreviate this class. So substitute equation 2 in equation 1. Okay, so uh, we have C, or I will write, no, substitute natin ang 2 dito. So equation 1, I will write first the right side part of it. So we have 6x squared, 6x squared plus 6 times x times h, but h is equal to 2000 divided by x squared, so just multiplied it by that equivalent. Okay, so our h is 2000, so 2000 divided by x squared. Okay, so now if you look at the right side class, how many variables you can see on the right side? How many variables? So there's only one variables remaining on the right side. Okay, so our left side now is still c, but this time c is a function of a single variable, which is x. Okay, so we have c of x equal to 6x squared plus 6x times 2000 divided by x squared. And we have here at the numerator x, so x, and you have denominator x squared, so x divided by x squared. So what will be our uh, equation now? So the equation becomes c sub x equal to 6x squared, 6x squared, then plus, so 6 times 2000, so we have 12,000. Okay, 12,000 divided by, so divided by x. Okay, or we can rewrite this as c sub x equal to 6x squared plus 12,000, and we can bring x up. So x understood to be, or to have an exponent that is equal to 1. So when you bring this up, so this will be to the power negative 1. Okay, so that is now our cost function. Now since we are optimizing, or we are solving these optimization problems, and the problem says that what will be the total cost that will give us the least, or what will be the total cost of the materials that is least. This means so minimum, right? So if you are going to solve for minimum and the maximum, like the one mentioned in the extreme value theorem, so we have to set the first derivative equal to 0. Okay, so that we can be able to find the maximum or the minimum value. Okay, so that is extreme value theorem. So in other words, we are going to differentiate this with respect to the given variable, which is x, and then set the derivative to 0, then we can solve for x. Okay, so differentiating both sides. So don't forget class, part of the process is to do differentiation. So you have to remember the differentiation rule. Okay, so differentiating both sides. I'll just abbreviate some of these words, class, to make it faster. Now differentiating both side with respect to x. Okay, so we have the derivative of the cost as a function of x, so with respect to x equal to, okay, apply the differentiation rule, so 6x squared So 6, then we can apply power formula here. So this will be 12x. Then this is a constant, and then this is in the form of x to the u. So taking the derivative of this, so we will apply the power rule. So power will go down and multiply it by the base and also this constant. So this is negative, so multiplied by 12,000, so that becomes negative 12,000. Okay, so negative 12,000 times x to the power. So n minus 1. So our n is minus 1. So minus 1 minus 1. So this is minus 2. Okay. Now, using the theorem, um, so we have to set this part here equal to 0. Okay. So set this equal to 0. So we have now, so this becomes 0 equal to 12x minus 12,000, and you can bring this x squared down, x to the minus 2 down, and this becomes positive. So this becomes positive x squared. Okay, then solving for x. So the way to solve for x is, of course, we have to transpose this to other side. So this is negative, no? So when you transpose this to other side, so that becomes positive. Okay, so this becomes positive. This becomes positive 12,000. Okay, let me change this. So 12,000 divided by x squared equal to 12x. Okay, so equal to 12x. Now to solve for x, you can multiply both sides by x squared, or you just cross multiply x squared to the other side. So multiplying both sides by x squared, so multiply ito ng x squared, so x squared divided by x squared, so this becomes 1 times 12,000. So on the left side we have 12,000. Okay, equal to, so the right side becomes, so 12x times x squared, so that becomes 12x cubed. Okay, and dividing both sides by 12, so 12,000 divided by 12, so the right side also divided by 12, so 12x cubed divided by 12. So on the left side we have 1000, and on the right side we have x cubed. Okay, now solving for x. So how will you solve for x? So to solve for x, we have to take cube root on both sides. So we have 1000. So taking the cube root of it, cube root of 1000 equal to, we have x cubed, then take the cube root of this. So cube root of x cubed is simply equal to x. So cube root of 1000 is 10, and cube root of x cubed is equal to x. So therefore, our x is equal to, so what is the unit? So x is equal to 10 inches. Okay, so this is one of the dimensions. Okay, so 10 inches. All right, now since we have already x, so we can solve for h, because we have x here, we have x, and what we need more here is just the h. Okay, so to solve for h, so I'll just continue it here. So to solve for h, we are going to substitute x equal to 10. So okay, so substitute x equal to 10 to our equation 2, no? Or in equation 2. Okay, so in equation 2 we have h equal to 2000 divided by x squared, so 10 squared. Okay, so 10 squared, what is 10 squared? 10 squared is 100, so it means that this is 2000 divided by 100. So what is 2000 divided by 100? So this is equal to, h is equal to 20. Okay, so h is equal to 20. So the unit here is in inches, or just simply in, no? Stands for inches. All right, so now we have solved the dimension. So therefore, so what is our conclusion here? Okay, so just make a screenshot of this class, because I will turn the page to the slide. Okay, so you have taken a picture already, or a screenshot of this side here. All right, so if already done, then let's go to the uh, slides. So I'll erase this. So these are the given, and the solution was shown in the screen, no? The screen that we have. Okay. Mm, so I delete this one. So okay, so this is the, actually this is the summary class now. Okay. Uh, so we have here the solution that we have done. Then after we obtain the value of x, the value of x, that is 10, and the h is uh, 20. So this is our final answer, class. Therefore, the dimension of the box that will give least total cost is 10 by 10 by 20. All right. So 10. So this is our x by 10. So this is also our x, and this is our h. Okay. So when you're asked for the dimension, your answer your answer should be like this: 10 by 10 by 10 by 20. 20. In other words, class, this is just the volume, because you can also write it as your dimension could be something like this. There is another way of writing the dimension. So dimension is like 10 by 10 by 20. Okay, so to check if your answer is correct, then the product of this should be the given volume, or equal to the volume that is the box that needs to accommodate, no? 10 by 10, so 10 by 10, 100 times 20, that is 2000. Okay, so this is our final answer, class, this one here. All right, so I think that's all for this part. There are a lot of exercises in this slide. Just please solve them. Just follow the procedure, follow the same thing that you have done. Okay, so if you look at the next slide of this, so you can see a lot of okay, so there are some exercises here. Try to solve them, class. Like, for example, we have here, find the two positive integers whose product is 36 if their sum is small, or their sum is as small as possible. So same thing, you just look for the first positive integer, then the second integer, then you express your sum. So how will you express your sum? And then take the derivative and set that derivative equal to 0, and you will get the answer. Okay, and another problem here. So you're also asked to solve for the dimension of the largest. So the word largest, small, least, so that give us a signal that we are now solving optimization problems. Okay, so that's all for today, class. Let's try to solve other examples that you can see from this PowerPoint. And there is one more example here that you can see detailed in the solution. You just study them and understand them. Okay, so that's all for today. And this is our uh, topic on or one of the applications of the derivative. All right, so thank you very much. Good luck to your uh, graded activities. Bye. Stay safe and healthy always. God bless.